Hello. This evening I'd just like to go over the technique you learned the night prior called complete the square. What I've got at the top is an example, and the underlined numbers are simply the things that were required to complete the process. So what I want to do again is talk about where those come from and then go through the remaining examples on the page. So it was complete the square, correct? We wanted to turn this, or at least part of this expression, into something that's perfect squared binomial, whereby we get this format for a quadratic function: y equals a times x subtract h squared plus k. Of course, all these examples, they're going to assume that a is 1, and that's actually necessary because you cannot complete the square until you make the a value 1. That's another issue altogether, so do not fret about that. Math 2 is going to stay 1. Okay, now, how on earth do we get this number? Right? Does it just come out of thin air? Do you just find the tree that says complete the square, pick me? No, this number is a special calculation, because at this point you realise the number you put here is going to multiply times itself. It's also going to be doubled to create this number. So what we're going to do, we're thinking backwards here. Okay, so I've got to double this number to get this number to go in the opposite order. I'm simply going to cut it in half. So 10 cut in half, 10 is 10. Cut in half, that means divide it by 2. That's going to be 5, right? And then we realise when it's in this format, the 5, of course, in both parentheses, it's ended up getting squared. So 5 times 5, yeah, that's 25. So we're going to square it. Alright, and the general rule for that, of course, that's where I came up for 25. What you have to remember for this bottom problem is b over 2 squared. You have the b, you square it, that's the number that goes in the box. Okay, it should be obvious why I put a square here, but something to think about later. Alright, so these first 4 examples, we are trying to convert to vertex form, so that we can see what the vertex is. So in this first example, b is 4, so we cut b 4 in half, that's 2. 2 squared is 4, so I'm going to add 4, and I'm going to subtract 4. Okay, that means this particular portion can now be factored as x subtract 2 squared. How to know it was subtract? Well, it's always going to be the same as this sign, right? This number is always plus, because when you multiply a number times itself, whether it's positive or negative, it ends up becoming positive, so it's plus. But this number has an effect on what you write here. It's always the same sign, because these have to add up to get that 4, that subtract 4. So minus 4 minus 3, that becomes minus 7, and from there we get the vertexes at positive 2, negative 7. Okay, moving on to the next example. b is 16, after 16 is 8, 8 squared, 64, and 64. Make sure you understand, I added 64 and then I took it away. It's like that rule when you were in grade school, when you'd pass someone in line and then that you'd have to let them pass you back so that it was fair and you weren't cutting. It's the same thing. Well, I suppose that's cheating, but nonetheless, we add 64 and then we take it away so that the net effect of this red stuff here I've written is 0. I haven't changed this original equation. So this particular portion becomes x plus 8 squared minus 64 plus 10, so that's going to be minus 54. Gives us a vertex at negative 8, negative 54. Okay. After that, b is 12, half of 12 is 6, square that, you get 36, 36, so the x subtract 6 squared minus 39. Alright, remember this part here, we're trying to see what makes that equal to 0. That actually finds the minimum of the parabola, because the lowest possible value we can get from something squared is indeed 0. That occurs at 6, and then this is simply how much we shift down from 0. So 0 subtract 39, negative 39. Okay, hopefully that's making some sense. If that was gone, this essentially shifts the parabola 6 units to the right. If you want proof, plug in 6 for x. You get 0. So 6, 0 ends up being the vertex. And then we shift it down 39 units. proving that, okay? Here the b is 1, sorry 2, half of that is 1, 1 squared, yep, still 1. So we've got x plus 1 squared from this bit, and then the negative 1 plus 10, ends up being a plus 9. So we have a vertex at negative 1, positive 9. Alright, the next task that I asked of you after watching the video and completing the practice was to use complete the square for another purpose, and that is to solve a quadratic equation. So if we look at this page, we try to follow this. This example is already set equal to 0. So that would of course be the first order of business had that not already been done for you. Okay. The second thing you notice, the 13's over here. In the next step, it's over here, and it's got the opposite sign. So what happened? I simply added 13, and that's what happened. Where'd the 49 come from? Well, that's of course half of 14, 7 squared. All right, so that is our complete the square number. Now look at how it's different from above. All right, you don't see the plus the number. You don't see plus the number and then straight away subtract the number. You see the number being added on both sides. So in your understanding of an equation, isn't that maintaining the balance of the equation, right? Okay, so this part here is going to factor as x plus 7 squared equals 62. How do we get rid of this squared symbol? Of course, we're going to use the square root, and that's how you end up with the next line. Now this bit may be a bit new to you, but I want you to think about something. If I take the square root of both sides, right, this bit could have been the negative, right? But I've known no difference because when you square a negative number, it becomes positive. So we've got to consider both possibilities that the square root could have been plus or minus. Now notice, that's not imaginary numbers. So plus or minus is outside, so it's okay. And just to illustrate this, let's think for a second. And I tell you, some specific number, when you square it, gets 9. Well, if you tell me x equals 3, I'll say, yes, that's correct. Sort of. That's not all. You see, x also equals negative 3. Here's why we have to put the plus and minus. So what I'm going to do, I'm going to rewrite this. I'm going to move the 9 over. So we're going to rewrite this as x squared minus 9. And now if 9 minus 9 is gone, that's equal to 0. What we've learned in class is that x and x, I can factor this process. X plus 3, x minus 3. Well, what does that show us? That shows us, that proves to us that x could be negative 3 or positive 3. When you square it, you get positive 9. So if you go backwards again, you've got to assume, okay, it could be plus or minus. All right, now that you've got an understanding for this rule and why the plus or minus is there, there's one final step to solve for x. We're going to subtract the 7 from both sides. And then now, instead of writing it back here, I'm going to slap it up front. So this means I've got two answers for a quadratic equation. It's negative 7 plus the square root of 62 and negative 7 minus the square root of 62. You see, that symbol means plus and minus. So two different answers. All right, how does that affect us in these examples? Well, we're simply going to complete the square. So what's already been done is that the 9 is moved over, so it's positive over here. Right? Half of 8 is 4, 4 squared, 16. But I've got to add it to both sides now to maintain the balance of the equation. And of course this will factor x minus 4. 9 plus 16 is 25. So what we've got to do from here, I wish I had my other pens, is take the square root of both sides. So we're going to get x minus 4 equals plus and minus, what was the square root of 25? 5. So x is going to be two different numbers. Right, we're going to add the 4, so we get 4 plus and minus 5. Well, I think you can figure out what those numbers are. 4 plus 5 is 9. 4 minus 5 is negative 1. We've got two answers. And again, hopefully you're making some sense of why we get two answers, because these graphically are parabolas. Parabolas can cross the x-axis or equal 0 exactly 2 times. Sometimes 1, sometimes none. But hopefully the two answers is making some sense to you because of the two x-intercepts. Moving on to the last one. Complete the square, move the 7 over. So we're going to complete the square. What number goes in the square? What is it? Half of 6, 3. 3 squared, 9. Okay, so x plus the square root of 9, 3. And 7 plus 9 is 16. So what I've got now, I'm going to move the square root both sides. So I've got x plus 3 equals plus and minus, what's the square root of 16? 4. So we're going to move that over. If you subtract the 3 to the other side, right, you see that's going to happen. We've got negative 3 plus 4 and negative 3 minus 4. All right, and you probably know that those answers are positive 1 and negative 7. Oh yeah, didn't we know that those would be the same answers? Positive 1. Well, let me rewrite this problem in the back. I'm running out of space. X squared plus 6x minus 7 equals 0. Right, that was the problem we just did. Go back and check. Wait, okay, I suppose I'll go back. Yep, that is it. So, don't we already know how to solve this? Oh yeah, it's x plus 7 and x minus 1, giving us answers of x equals negative 7, x equals positive 1. Were those not the same answers that we produced using this method? Here's the 1, negative 3 plus 4, yep, that's 1. And negative 3 subtract 4, yep, that's negative 7. So I love it when this happens. You probably heard me say this in class. When math justifies math, it's a beautiful thing. Don't come in with any blanks in the morning. Please bring me your questions.